Welcome to Unlock Layouts. Today in this video lecture we are going to discuss the internal cross-sectional layout view of ESP8266 chip. So ESP8266 chip is the Wi-Fi adapter, and as well as it's a kind of Wi-Fi chip. So now we are going to discuss the internal layout structure, how the layout style is there and what kind of methods they have used and what kind of pad they have used inside the chip. So let me start the video and let me explain, and I'll try to give you the clear picture of the ESP8266 chip die layout. Let's start the video. So here we have a full chip dissection view of the ESP8266 chip. So we have so many interconnects, like they have used inductors and they have used transmitter sections, receiver section, and so many coupling capacitor sections, and as well as we have a pad section, and as well as they are used some of the shielded rings. So usually we'll call that is as a shield ring. So everything they have implemented in the ESP8266 Wi-Fi chip. So usually it's a Wi-Fi chip which is fabricated or designed in the year of 2013. So I don't have any idea about what technology they have used here, and also which foundry the chip is made of. It's a normal Wi-Fi chip which is working on 2.45 GHz, and as well as the internal chip consists of TCP/IP stack of the internet modem connectivities connections also they have integrated in this. So today what we are going to discuss, so the layout structure and then the internal cross-sectional view of entire layout of this ESP8266 chip. So let me start from the left corner here. So what you are seeing in the left corner, hope you can able to follow my mouse pointer. See here, whatever you are seeing in the right corner place, this one. So this is called a shielded ring. So usually they will call the shield ring. Okay, so this shield ring will be used for the entire chip. So from the right hand corner to the shield ring will be extended up to this right end, then left end, as well the top and bottom, everywhere. So entirely the die will be covered with this shield ring structure. So shield ring usually they will use for the isolation purpose, and other than that we have so many advantages if you are started using the shield ring usually. Because what happened at the time of splicing your die, so usually they want to cut down the die from the wafer. So depends on the fabricational type, like whether it's a 100 process or 11 process or 111 process or 101 process. There are so many cutting options are there. If you want to splice the chip from the die, there are so many options. So they used to follow 110 fabricational type or 111 fabricational type. So there are they have so many types. So this shield ring usually they will use at the time of cutting your chip and splicing your chip from the die. So it will protect your entire chip from the splicing. So that's the main reason why they are using this shielded ring. So other than that, they have other reasons also, like entirely the chip is shielded with the seal ring. So the seal ring, like it is like providing some additional isolation. So we'll discuss about the seal ring in the future video. So now I want to discuss about the cross-sectional view and the layout style and the placement of the device and everything I wanted to show you. Because see, this video or this image will give some better understanding about the internal cross-sectional view and as well as the layout style of the chip. Because usually we used to work in the sub-block level. Most of the time we don't see what is the top level layout of any of the layout. So it depends on the experience level. Maybe some of the peoples will work in the top level integration, and under 5 years to 10 years experience people. So it depends on the project. You may get a chance to work in the top level, which means the full chip level, sometimes not. So now in this image we can able to conclude, or we can able to come some better ideology and better understanding about the layout structure. So now let me start from the same right hand side. sorry, left hand side. So whatever you are seeing here in the left hand side, some, you know, the wider ring, it is called a seal ring. So seal ring is used for the isolation purpose. Then there are some square boxes here. So these square boxes are the pad connection. So in this ESP8266 die, totally it has a 17 GPIO. So GPIO means general purpose input and output pad. Okay, so that is called GPIO. So here the GPIO voltage ratings are 3.2 voltage. So, you know, if you want to know about the GPIO, what is the functionality of GPIO and layout of GPIO, I'll try to put in the separate video section for the GPIO. So now, just for the sake of simplicity, we'll try to understand whatever the square box you are seeing here, everything, all the square box are like a pad connection. So from the pad, from this pad, by using the wire connection, wire bond, or, you know, any other, there are so many types of bond connections are there. So usually most of the time they will use wire bonding. So from the pad they used to take a wire bond, and this will be connected to your outside of the chip. So outside of the chip means, suppose if you are using some you know, depends on the packing of the IC, like ball graded array and, you know, BGA, dual in package or single in package. There are so many packing types available for the, you know, IC packing. So depends on the packing, they used to take bonding from here, like wire bond or metal bond. Sometimes they will use gold as a bonding. So they will take a bonding from here. It will be in, you know, interface, the connection will be connected to the outside of the world. So this is your die level connection. So outside of the packing connection we don't have any figure now. So we'll understand whatever square box you are seeing here, everything is the input and output pad, nothing but the GPIO. Okay, so see, this pad they are not using anywhere, because the pad is not connected anywhere from the routing. I'm not seeing any you know, routing here from the pad. So this is like the ideal pad. They are not using this pad, this is like a dummy pad. So on, if you are coming in the right hand side, see here, there are some pad which is taking some connection here, some wider metal connection they have taken here. So which means this wider connection may be power, like VDD, or maybe ground. There are only two cases. Okay, because most of the time power connection they used to keep always as a wider metal. So from the pad they have taken, see, three different metal connection they have taken, the maximum metal width which is allowable to fabricate. So depends on the foundry and depends on the technology, the maximum width of the metal will be determined. So now they have, you know, divided this into three portion of the metal, and finally these three portion of the metal is connected to the wider metal. See, from the wider metal, this wider metal is going and connecting everywhere inside the chip. Okay, so see, hope you can able to see this. So from this wider metal they have taken the tap. So from the tap here, whatever internal circuitries are there, like it may be a diff pair, or it may be a current mirror, it may be any kind of logic circuits, it may be anything, amplifier or whatever it is, but the power connection they are taking from the pad. Same way here they have another pad, so this we can consider as a ground. It may be VDD or ground, there are only two cases. So whereas here also they have followed the same structure, they have separated into three different metal lines to connect the pad. So from the pad they have taken the wider metal, and this wider metal is going all the way from here, which is connected to everywhere. So this, maybe this I can tell, like the right side pad, whichever it is there in the right hand side, this can be a ground. So because see, most of the connections which is going here, it is not connecting to any of the device. So outside of the most of the connections are outside. So maybe we can consider this as a, I can consider this as a ground. I would say it's a ground. If not, we can tell it's a power signal also. We don't have any clear idea about whether it's a power or ground. But the distribution of the power and ground, see the style of the distribution in the layout. They have taken some wider metal. So from the wider metal, this is like the main power bus. So from the main power bus, almost all your internal circuitries are taking the internal power. So from the small metal, see here, from the wider metal they have taken a small metal connection which is connected inside of your some sub block. So in this way only maximum time they will distribute the current and as well as the voltage. So this is like the power bus. So then I wanted to show you few additional pads here. See here, there are so many pads from the power to another next to that we have another pad. So there are different types of input signal, like we have a VDD, VSS and clock signal and data signal, and so many synchronized signal, unsynchronized signal, reference signal. There are so many signals, but see the style of the pad how the way they have taken the power, like the connection from the pad. So this is how they used to take the power, or they used to take the signals from the pad usually. Okay, so whatever you are seeing, the small like small dots, so these are like via, see wherever you are seeing the small black color dotted lines, those are all like via, because they used to stack all the metal from the top metal to the bottom metal usually for power. So in order to connect all the metals, so if you want to integrate these via, if you want to integrate 2 or 3 metals to maintain the EM and IR drop, so here whatever you are seeing the small dotted lines of black one, so those are all like simply it's a via. Okay, so then we'll move on in the left hand side laterally. See, now almost the top side all the things are like pad connections only. So it's a general purpose input output pad. It may be input signal or it may be output signal. They can use it for any functionality because it's a general purpose IO. Okay, so then we'll come to the middle section. See, this is a kind of inductor. I don't know like how many people are worked in the inductor. So this is a kind of inductor structure. So usually inductor will have this kind of structure only. They used to try to fabricate the inductor. So there will be a lot of empty space between this inductor. Usually we don't place any additional devices like MOSFETs, transistors, or any resistor, capacitor, whatever active and passive devices. Usually we don't keep anything nearby to the inductor, because inductor is the signal, whereas it can be act as a transmitter or it can be act as a receiver, because both the functionality inductor can do. Okay, because since it is a Wi-Fi kind of a pad or a die, so this inductor, they can use it for the transmitter also and they can use it for the receiver also, because this Wi-Fi chip is working under 2.45 gigahertz free spectrum frequency of Wi-Fi. Okay, so around the like the inductor, see there are some additional vias. So these are all like like the body connection or substrate connection to the inductor. So because even inductor also sometimes they used to keep the additional body connection, so to provide some noise or to give some isolation or to give the free path to, if there is any noise also, the noise will be injected easily to the ground. So that's why usually they don't keep any devices around the inductor, and all around the inductor they have some additional vias. So these vias will be connected to your substrate. So substrate is nothing but your ground connection usually. So then other than that, see here in the left hand side also we have some inductors. So wherever you are seeing the inductor, see most of the inductors are separately isolated from the other devices, because there is no other devices nearby to your inductor. So this is how usually inductor we used to place. So on, see here you have some spiral inductor. So see, hope you can able to see the difference between the this bottom inductor and as well as the right hand side inductor. See, left hand side inductors are spiral inductor, whereas they are using the single metal. So from the single metal it is created some kind of spiral structure. So finally they have taken a single net as output, whereas here in the another inductor it has a 2 input signal. One is the input and another one is output. So here they will use 2 different metal, like M10 or M9 or M11 or M12 or M5 or M6. So they will use 2 different metal here. So that's why this structure of the inverter is completely different. This structure of the inverter is completely different. Okay, there are different types of inverters are available. Different types of inductors are available. Okay, so on. We have another pad here in the bottom. Here we have another pad. Again we have another large inductor is there. So hope you can see the top level view of the inductor here. See this top side we have some input connection. So we have 2 metals which is routed in the top, and another 3 metals are routed in the bottom. One is like main metal, because they have connected with the wider metal line with lots of via. So it may be a power or input signal, and another whatever left hand side is there, that may be a ground signal. Okay, so we can consider, because see we cannot able to trace the complete routing structure here. So we can blindly conclude some idea like how the inductor will be fabricated in the top level. So this is how the inductor will be fabricated in the top level, whereas see here you can able to see a small inductor. See, this is small inductor. It has having only one input signal and 1 output signal. Only it's a very small inductor. So same way here we have some analog blocks, because here most of the things are, see this is like source routing and drain routing, and so I'm not able to see the clear picture of the device in this layout, but we can consider this is like maybe some analog blocks or digital blocks. because this ESP8266 consists of some microprocessor, and as well as it has the internal memory of 32 kilobits of memory allocations are there. So it may be a digital blocks or analog block, so on. If you are coming in the bottom level, most of the things are inductors only. See here, there are some kind of MOSFETs. So it is like a grouped MOSFET, like source connection, drain connection, source and drain. So it is like a kind of some it may be a diff pair or it may be a single device, but this is the MOSFET, 100% it's a MOSFET. Okay, so it's a some kind of device. So then almost in your layout, 70% of your layout is consist of capacitor. So whatever you are seeing in the bottom, all the things are like completely it's a capacitor connection. So everywhere whatever you are seeing here, everything is the capacitor. So almost in the ESP8266 chip, completely almost like 75%, 50% of the portions are filled up with your capacitors. Okay, so then other than that, see here there are some another additional device, whereas see here in this portion you are seeing some small metal via, which is floating metal via. So this is not exactly via. So in order to improve the density, they used to add the density metal here. So this is like the density fill up metals. It may be any metal like metal 1, metal 2, metal 3 or whatever it is, but this structure here, hope you can able to follow my mouse pointer. So here there are some floating via kind of structure. So these are like density fillers, okay, metal density fillers. So on here in the bottom side, see here you can clearly see in between the capacitor to your pad, okay, this is a pad, and in between your pad to a capacitor there are some via structure, a kind of structured via. So actually this is not the via, this is the density metals. Okay, in order to avoid density, so they used to fill the metal here. So this is like the density metals. Same way I'll come in the right hand side. So here hope you can able to see. So this is our seal ring structure, because seal ring have a kind of structure only. So this is the 100% seal ring. So on top of the seal ring we have some via structure. So this via structure is also for density fill up. Okay, so these are like density metals. So let it be any metal like M1 to M2 or whatever metal they are using. So everything. So from the right hand side, wherever my mouse cursor is there, all the metals they are used for density metals. Okay, these are all just for the density. Everything is density. So right hand side, whatever you are seeing from the bottom of the bottom of the seal ring to the top of the pad, everything is the density fillers. Okay, even though sometimes see here also in the right hand side, in the right hand corner next to this seal ring, they have used the density fillers. So these metals are density fillers. So then see the connections here. Like usually they don't use a single via or single metal line for the capacitor connection. They have taken 4 metal connections here. See 1, 2, 3, 4. 4 metal connection is connected to the capacitor, and 4 vias are connected to this capacitor, because usually they don't take a wider metal. They used to take multiple metals in order to, it may be a fabricational problem and it may be a lithography limitations. Because of the lithography limitations, they used to always take a wider metal length which is possible for the DRC and which is possible to fabricate. So they used to take multiple metal connections here. See 1, 2, 3, 4. Almost they have taken 4 metal connection, and then the rest of the things here, maybe you can able to see some of the routings here. So I am not able to see a complete internal cross sectionals here in the ESP8266 chip die. Maybe I'll try to collect some other die chip design. Okay, so I'm trying to collect some other die chip images. So once I got those images, I can able to clearly explain you how the source and drain connections are there internally. Okay, so this is like the very older technology layout. See, whereas here you can see some layout, like here. So one is like source connection, and top of the one is like drain connection. So whatever the top it is going, so these twos are like source connection, because this is coming and connecting to the main power. So main power may be a VDD. So from the VDD they are trying to give all the VDD to the source connection, and middle they have taken the drain connection. So this drain is connected to the another device of the drain. So then again they have a source connection in the top and bottom, and they are trying to take the source connection from the different metal. See here you can clearly able to see this structure. It's a MOSFET structure only. Okay, it may be a diff pair or it may be any other device, but it's a source and drain connection. Okay, let me try to zoom in somewhere else. Okay, so most of the device pictures are not very clear, but you will come to know some ideology of the fabricational design and the way how they will design the chip. See, in the bottom of the chip they have mentioned the chip name. See the wafer cutting edges. So in the left hand side you can able to see some CD, some text layers are there here, C and D. So which means next to this seal ring they used to cut the die, because usually in the wafer they used to fabricate millions of chip. So each and every chip has to be spliced and each and every chip has to be cut and they need to take away, right? So this is how the cutting portion will be there in the edges of the chips. So hope I have given some more other details about the chip die structure. So if you want the picture of this chip die, I'll give you the download link in the description. If you want, you can download and use you do your own explorations in the chip. Okay, so if you want, I'll give the download link in the below. Okay, you can directly go and download the entire image of this chip die. So now here this is our ESP8266 chip after packing. So hopefully you can able to see how small the chip is there. Almost in the x directional it is almost like 18 millimeter, that's all. So not even 20 micrometer, it is almost like, so here it is 15, 16, 17 micrometers, that's all. Sorry, 17 millimeters. Okay, 17 millimeter cross 10, 12, 13, 14 millimeter. So 14 millimeter cross 17 millimeter is the overall chip size. But inside the chip, whatever before we have discussed, like there are so many microprocessors and there are so many RF transmitters and receiver, because the ESP8266 has a RF and mixed mode layout design, because usually the modem consists of analog to digital converter and digital to analog converter, because it's a demodulator and modulator, right? So we need to convert the digital signal in the form of analog, again analog signal in the form of digital. So that is the functionality of modem usually. Other than that, it has an internal microprocessor, so which is working under almost like 182 megahertz frequency somewhere. Okay, that's the frequency range of the microprocessor, but I'm not very sure, but it is lesser than 200 megahertz. The operating frequency of the internal microprocessor is 200 megahertz, lesser than 200 megahertz, that's all. And then the operating voltage of this IC is like 3.3 volt. Okay, so whereas before we have discussed so many things in the IC, but everything is combined together and then it has packing. So it is this is the packing style of the IC. Okay, so inside the the packaging style they used to keep the die. Okay, so whereas we have discussed in the before, right, the die is kept inside the chip, that's all. So this is how the packing style will be there for the usually chips. Like the foundry can go for any type of packing, like we have so many types of IC packing is available. So this is like a normal packing. Okay, so and then see, you can able to see the overall PCB size. It's almost like 18 cross 20 millimeter cross 18 millimeter is the, including the PCB size, it has the 20 millimeter cross 18 millimeter chip area. Okay, the overall size of the chip, that's all. So just imagine how smaller the chip is, and within the chip we are working, like we are trying to implement, we are trying to keep millions and billions of transistors here. So without any fabricational error, the chip has to work. So I hope I have given some valuable information to you in this video. Thank you for watching my video. If you like this video, please click like button and share this video to your friends. For more details about this video, please contact us to my email ID and follow us on my Facebook page and Twitter page, and kindly subscribe our channel and don't forget to click the bell button.